All right, let's take a look at the nature of solutions. In the warm-up, it says, below is a list of common substances. Classify each as a pure substance or a mixture by placing a check mark in the appropriate column. Okay, so for car exhaust, that's a mixture. Tap water, well, you could argue that that's a mixture because there are some salts dissolved in it. If it was distilled water, I would consider it a pure substance. Carbon dioxide, pure substance, because that's just a compound. Freshly squeezed orange juice, I would argue that that's a mixture. Stainless steel, that is a mixture of different metals. It's actually a solid solution. And then tea is a solution. And then diamonds, that's purely carbon. So that's a pure substance. Cigarette smoke would be a mixture. Now, in this chapter, we're going to be looking more closely at specific types of mixtures known as solutions. And what I want to do is I want to go over some of the common terms here. So solutions are homogeneous mixtures that exist in one phase. So no matter where you are in the sample, it's always going to be uniform. And you can have solid solutions, liquid solutions, gaseous solutions. And a common example of a liquid solution would be ocean water. That's where you have salts and other substances dissolved in the water. There are two components of a solution. There is a solute and a solvent. The solute is dissolved in the solvent. It is typically present in a lesser amount. The solvent does the dissolving. It is usually present in a greater amount. So for salt water, the salts are the solutes and the water is the solvent. Now, if I am talking about liquids mixing and other liquids, if they mix uniformly and we get a homogeneous mixture, then we would say that the two liquids are miscible with each other. And this typically happens when they share similar intermolecular forces. If we're talking about mixing water and alcohol, they mix uniformly. You can't tell where the water is and where the alcohol mix because they just mix right away. If I mix something like oil and vinegar, they do not mix. So those two liquids would not be miscible. If I'm talking about immiscible liquids, these do not mix when you are combining them. So vegetable oil and water do not mix. They exist in two different phases, and you can see them, those different phases separated. And so immiscible is what you are allowed to use when we're talking about liquids that do not mix uniformly with each other. A lot of these examples of solutions that exist in different phases we've gone over in the past. Air is a gaseous solution. Alcohol and water, a liquid solution. Alloys like brass would be a solid solution. If you take a look at the quick check, it says you classify the substances as, in the warm-up, as pure substances or mixtures. For the substances that you classified as mixtures, list the ones that are solutions. So solutions look the same throughout. So this would be tap water, stainless steel, it's a solid solution, and then tea, which would be a liquid solution. Okay? Now, many chemical reactions occur in solutions. If the solvent is water, we call it an aqueous solution. And there are important reactions that happen in your body that we may, that happen every day, and they are considered aqueous reactions. And a solute that dissolves in a solvent is known as soluble. So you use soluble when you are dissolving a solid in a solvent, or solid in water, typically. So sodium chloride, table salt, is soluble in water. So we would say that table salt is soluble, okay? Insoluble is what you will use when you are talking about a solid that has low solubility in a solvent or in water, okay? There are a lot of different units for solubility. This is the maximum amount of solute that's going to dissolve in a certain amount of solvent at a temperature, because if I increase the temperature, I generally increase the solubility for salts. So we have molarity, grams of solute per milliliters of solution, grams of solute per 100 grams of water. You'll typically see this on a graph. And then ppm, which is parts per million. If the solubility is given as molarity, this is known as the molar solubility. So let's take a look at the next page here. In the sample problem where they ask you to calculate the molar solubility, you have to convert grams per liter to moles per liter. And you know that you can convert grams to moles by dividing by the molar mass of the substance, which they've done here to give you molarity. So we're going to do something similar here in the practice problems. So let's take a look at number 1. The molar solubility of strontium carbonate is 2.4 times 10 to the negative 5th molarity. Now, molarity is moles of your solute, which in this case is strontium carbonate, per liters of solution. So they want us to convert this to grams per liter. So you can convert moles to grams by using the molar mass. The 1 goes next to your moles of strontium carbonate, and the molar mass of your strontium carbonate will go here, which is 147.63. So when you multiply across, you're going to get 3.5 times 10 to the negative 3rd grams per liter, because moles is going to cancel. For number 2, it says the solubility of silver arsenate is 1.4 times 10 to the negative 6 molarity. So we're going to convert this to liters. I'm sorry, not to liters, to grams per milliliter. So we're going to convert our moles to grams here. So the number that goes here is the molar mass, which is 462.53. So moles will cancel. And then liters is going to go here and milliliters down here. So the 1 goes next to milli, 10 to the negative 3 goes next to liters, so you can cancel out liters, leaving you with grams per mil. So this will end up being 6.5 times 10 to the negative 7 grams per milliliter. Number 3, if 500 mils of a saturated solution of silver chloride contains 9.3 times 10 to the negative 4th grams, what is the molar solubility? So we're solving for moles per liter. So I need to convert my grams to moles, and I'm going to do that by dividing by the molar mass of silver chloride. Somehow I am missing my molar mass in my book, so I need to calculate this really quickly. So this is going to be on the back of your book. Silver is 107.87, chlorine is 35.45. You're going to get 143.32. And then we need to have our milliliters converted to liters. So I'm going to do that in a one-step metric conversion here. I could have just moved the decimal 3 places back, and that would give me 0.5 liters. You can do that if you want. So this is going to be 1.3 times 10 to the negative fifth. Just double checking my math really quick. Yeah, times 10 to the negative fifth molarity, which is your molar solubility, okay? Okay, now, number 4. The solubility of copper 2 iodate is 2.6 times 10 to the negative third molarity at 25 degrees Celsius. And they're giving you the temperature because the solubility changes with temperature. What mass of solute is present in 250 mils of solution? So I want to convert my liters. This is really 0.25 liters, so I'm going to put that here on the up diagonal to cancel my liters. I technically didn't need this 0 on the end because it's not significant. And then I'm going to go ahead and convert my moles to grams. So the molar mass is 413.35. And I'm going to get 0.27 grams. Okay, now let's talk about whether or not a solute will dissolve in water. Okay, now ionic compounds are made of cations and anions, and if that solid doesn't dissolve in the solvent, usually the solvent is water for us, then it's going to be insoluble. Carbon, for instance, solid carbon is insoluble in water, and some salts are going to dissolve better in water than others. And to predict the solubility, we're going to look at the solubility table on the next page. Now, when we look at this table, we have to note a couple of things, and this is going to be different than a lot of textbooks in the United States. The word soluble means that more than 0.1 moles of the solute will dissolve in a liter of solution at 25 degrees Celsius. And this is what I want you to star. Low solubility, which in the United States, a lot of introductory chem books just say that insoluble means everything else. But here I'm specifying that low solubility means less than 0.1 moles of the solute will dissolve in a liter of solution at 25 degrees Celsius. It does not mean that the substance is insoluble. It just means very little can dissolve, okay? And when you're looking at the table on the next page, you will see that at the top, they've listed anything with an alkali ion. Alkali ions are lithium, sodium, potassium, rubidium, cesium, francium, which they will refer to these collectively down below as alkali ions. Any compound with an alkali ion is soluble in water. Any compound containing a hydrogen ion, soluble. Anything containing the ammonium ion, soluble. Anything containing the nitrate ion, soluble. So all of these compounds would be soluble in water with any of these ions, okay? Now, down here, if you have a chloride, bromide, or iodide ion with silver, lead 2, or copper 1, then these would have low solubility. So some examples would be AgCl, or AgBr, or AgI, okay? You could also list PbCl2, PbBr2, PbI2, okay? Or CuCl, or CuBr, or CuI, okay? Now, any of the sulfate-containing compounds with a silver ion, calcium, strontium, barium, or lead 2 have low solubility. That means something like Ag2SO4 or CaSO4, for example, or SrSO4. Those have low solubility. But with all the other ions with sulfate, they're soluble. Sulfides, they have low solubility with everything unless it is sulfide with any of these ions. So if you have BAS, that is considered soluble. If you have SRS or CAS or NGS or BES or NH4 with S, those are all considered soluble, okay? Hydroxides, those are soluble if it's NH4OH, for example, or if it's SrOH2. All the rest would be considered low solubility. Also, the alkali ions with hydroxide or hydrogen with hydroxide is considered soluble. For the phosphates, carbonates, and sulfites, okay? If they're with the alkali ions or hydrogen or ammonium, they are soluble. All the rest have low solubility. So for instance, if you have H3PO4, that would be soluble. If you have an alkali ion like sodium with carbonate, that would be considered soluble. Okay, let's go on to the quick check down here. Here it says, what is an anion? Well, that's a negatively charged ion. It's a cation, a positively charged ion. And when you're looking at salts, the cation comes before the anion. Salts containing which cations are always soluble? Well, if you look up above, the alkali ions, those are all cations. They all form positive 1 charges. Also, if you have salts with a hydrogen ion or the ammonium ion, these are always soluble. Salts containing which anion are always soluble? That would be anything with the nitrate anion. Salts containing which anions have low solubility the most often? You'll notice if you look at the phosphates, carbonates, and sulfites at the very bottom, those tend to have very low solubility because there were only a handful of substances that they were soluble with. Okay, let's go to the next page. And let's look here. In the sample problem, it says silver chloride is soluble in water, or does it have low solubility? Well, if you identify the anion in the salt, so that would be the chloride ion, which is Cl-1. You want to look on the table for Cl-1, which I will show you back here. Here is Cl-1. And when it's with silver, it has low solubility. So AgCl has low solubility in water, which means its solubility is less than 0.1 molarity. Okay, let's look at the practice problems. For the following salts, use the solubility table to predict whether they are soluble or have low solubility. Okay, so for sodium chloride, well, sodium is an alkali ion, and these are soluble in water. So that means that this would be S for soluble. And when it has an S for soluble, if you have this in a chemical formula, that means there would be an AQ after it, denoting that it's soluble in water. Calcium carbonate, carbonates with calcium, which is in group 2, it's not an alkali ion. This has low solubility. So if you were forming calcium carbonate in a chemical reaction, I was asking you to write it out. Since it has low solubility, it would technically be a solid, denoted as a solid. Copper 2 chloride. So if you look at the chlorides on the table and you look for copper 2 is not listed as one for having low solubility. So this is soluble and it would be dissolved in water. Aluminum sulfates. Sulfates are soluble with aluminum, so that has an S. Barium sulfide, soluble. So that would also have an AQ after it. Zinc sulfite. The sulfites have low solubility with zinc. Ammonium hydroxide, that would be soluble because anything with the ammonium ion is soluble in water. Cesium is a group 1 metal, so the alkali metals are all soluble in a compound. Copper 1 chloride. Chlorides and then copper 1 have low solubility. And then chromium 3 nitrate, all nitrate containing compounds are soluble in water. All right, saturated and supersaturated and unsaturated solutions. An unsaturated solution is when the solute is completely dissolved in the solvent. Okay? So for instance, if you're making a salt solution with table salt, you put a little bit of NaCl in the water, which is your table salt, and it just completely dissolves. It's unsaturated. If I add more and it continues to dissolve to a certain point as I add the sodium chloride and no more will dissolve, the saturated solution is where no more solid will dissolve, and there has to be, please star this, there must be undissolved solid in the solution. Okay, everybody forgets that. Now, we can have a supersaturated solution if you got more dissolved solute than there would normally be to dissolve in it. These are super unstable, and they prepare these at higher temperatures, and then they slowly cool the solution down. So you take a look. Here, this is showing you that if you have a supersaturated solution of sodium acetate trihydrate and you slowly pour that onto a plate, it is so unstable that it will immediately start to crystallize and the solid will reform.